Brandon, give it a try. There's a high chance that you will like it.
There's a lot of people down in the Sneed Hall that like to play D&D in the main lobby area.
To be honest, I didn't know about D&D until I came here 4 years ago. In Iran, that's not a big deal. But actually, a friend of mine, when he saw that I'm really interested in Lord of the Rings and stuff like that, he suggested, "Oh, you're gonna probably like this," and I did. It's pretty amazing how the storytelling can be turned into a very multi-facet game.
Yeah, I can imagine.
Yeah, just make sure that you find a good dungeon master.
Wait, are we taking a break?
Yes, until 9:20.
Okay.
I used to play Counter-Strike, but not anymore, Ajibek. Well, plenty. It's not been that far. I've been there 4 years ago, but then when we got here, the travel ban happened, so we couldn't go back. But I remember many things. Favorite food? Definitely kebabs. We have plenty of different kinds of kebabs with different types of meat, and that is still my favorite food. What is gyros? Or gyros? Let me check. Oh yeah, and any type of if you are referring to Counter-Strike as I'm Googling it, let me check. Oh no, gyro is a dish. No, that is not Iranian. That is probably Greek. Yeah, that is a Greek dish. It looks good though. They have very good dishes. No, not really. To be honest, from the food culture side, Turkey, Greece, Iran, Lebanon, Armenia, they share some of the good stuff, but then there are certain differences in detail. Yes, Dr. Cleveland. In Turkey, they call it the doner kebab, and it is amazing. It is amazing.
It's pronounced doner.
Doner, yeah.
And you can find
Yes,
it.
sir.
You can find it all over the world. I have a photograph of myself in Tokyo by a doner kiosk out in the street. I was stunned to find that in Tokyo.
Yeah, that just fat dripping all over it.
And it wasn't made with some sort of Japanese fish disguised as doner meat. It was the proper food.
Brandon, masal is not an Iranian dish. It's a village in Iran, and it is very beautiful. So if you actually Google it up, you will see some amazing photos of it. Max, about last lab, when you get the different plots, we basically want you to give us a brief explanation on what was the difference between running that experiment for 10 times, for 100 times, and for 1,000 times. It's not anything complicated. So just look at the plots and see what is the difference and why are you seeing that difference. Masala is Indian. Masala is Indian, not Iranian. Exactly, yes. Actually, unfortunately, we do not have like a Persian restaurant in Lubbock. But if you happen to be in Austin, in Dallas, San Antonio, and Houston, they have some not very bad Persian restaurants over there. But nothing will be homemade. So. Cool. Let me know what you think about it, Brandon. Have quizzes been added recently? I don't think so. Dr. Cleveland, have you added any quizzes recently?
I don't think so. The program tells you when I add something, make it available. So if you ever have that question, just log into Blackboard for a few seconds.
We're still devastated by your midterm exams, so we've decided not to give you any more quizzes for a while.
Or we're just lazy. Could be that too. Or doing other things.
Soon, Liana, soon. I would say probably in about a week. So how many participants we have? 54.
Not bad.
Okay. Okay, so it is 9:20, and we are going to begin our lab. I'm hoping that you have all downloaded the file lab11 underline class version from the link on your blackboards. When you do, you will see a notebook pretty similar to what I have in front of me, even though I have made a few changes on mine. I will explain them as I go on. In the first cell in your information cell, as always, please add your name, your R number, the hex code, the title of the notebook, and the date. And in this lab, we are going to talk about probabilities and work on a few examples on computing probabilities of different events, and then asking you to work on some as your exercises. So before we begin, there are a few terms that I want to go over. Experiment, outcome, sample space, event, and probability. So by experiment, we mean an occurrence with an uncertain outcome that we can observe. So any event that can have multiple outcomes and we are not certain of that outcome can be considered as an experiment. Rolling a dice, drawing a card, drawing a ball from an urn, even the Russian roulette, these are all experiments because you know that it will have an outcome. It can either be a binary or a multiple possible choices, but you are not certain about that outcome. So that will be an experiment. The outcome is defined as the result of an experiment to one particular state of the world. So if I roll a die, thank you, Rami. Yes, picking a car or a ghost from 3 doors. That yes. I'm happy to see that the goat and the car example is sticking with you. If we go and roll a die, how many possible outcomes do we have? Waiting for your answers. 6, exactly. So 1 is an outcome, 3 is an outcome, 5 is an outcome, 4 is an outcome. And the total combination of these outcomes is the sample space. So the set of all possible outcomes for the experiment is referred to as the sample space. When I am rolling a die, my sample space is equal to 6. When I am doing a Russian roulette, what is the sample space? No. With Russian roulette, the outcome is either you get the bullet or you do not get the bullet. So you do have 6 chambers on the revolver, but the outcome of the experiment from the players. Pardon?
It's 2. Dead
exactly.
or alive.
Yes.
But the probabilities
I either die and get the bullet, or I survive and get to live another round. An event is a subset of possible outcomes that together have some property that we are interested in. So let's say that I'm rolling a die and I'm interested in getting a number greater than 3. So while my sample space is still 1, 2, 3, 4, 5, 6, my event or the part that I'm interested in will be 4, 5, 6. So that will help us to define the probability. The probability is defined as the number of favorable cases, the cases that will meet our requirement and condition, divided by the total sample space. So in the example that I gave you, what happened? Okay. So in the example that I gave you, I roll a die, and I'm interested to know the probability of getting a number greater than 3. What will be the probability?
One half.
Exactly, because 4, 5, 6, we have 3, and the total sample space is 6. So 3 over 6 will be 1 over 2 or 1/2. So about these terms, do you have any questions? No? Okay, cool. So let us move on. Here I am bringing in my external libraries that I'm going to use. NumPy, Pandas, Matplotlib. You are familiar with all 3 of them. Example 1. In a game of Russian roulette, the chance of surviving each round is 5 over 6, which is almost 83%. Using a for loop, compute the probability of surviving. So first, can you tell me why the chance of surviving is 5 over 6?
Because of 5 empty chambers?
Exactly. So you have 6 chambers, you have 1 bullet in them, so the probability of surviving will be to not get the bullet. So 5 of those that are empty are the ones that you're interested in. So that is given in the question. Now we are asked to compute the possibility of surviving for 2 rounds, for 5 rounds, and for 10 rounds. Let's see what I've done here. So first, I have created an empty list for my number of rounds and an empty list for my probs. What I'm doing is that for the first case that I want to compute it over 2 rounds, I'm saying, okay, for I is my counter, in a range of 3, which will basically go 0, 1, 2, I first want to append the value of I to my list of n rounds, because I'm counting my number of rounds. And I want to append 5 over 6 multiplied by I to my props list. So initially I had 2 empty lists. Using this for loop, I'm adding values. So can you tell me what is happening here? Why I'm taking 5 over 6 to the power of I?
Because for each round you have to multiply your probability by 5, 6.
Why?
Because you spin it every time.
Yeah.
Exactly, because in order for me to survive the second round, I need to first survive the first round. So the probability of me not getting the bullet in the first round multiplied by the probability of me not getting the bullet the second time will give me the probability of surviving after 2 rounds. Does that make sense?
Yes.
Cool. So, good. If we run this, at the end of the for loop, I'm converting everything to a data frame. I'm calling that RRDF, Russian roulette. You can name it whatever you want. And it will have 2 columns, number of rounds and probability of surviving. The first row is basically telling you that if you do not play the game, you have 100% probability of surviving, which is the case if you're smart enough and not play the game at all. But as you start playing the game, in the first round, you have 83% chance of surviving. In the second round, it goes down to 69%. Why is it going down?
Because you're running out of your luck.
Kinda, yes. Because even if you think about it, the first time you will get lucky not to get the bullet, but you have 83% chance for that. The more you try, actually your risks of getting the bullet is increasing, which means that your chances of survival are going down. Exactly, Rami, exactly. So then we were asked to check that for 6 rounds. And when you do that, you see that the probability keeps going down. And from 69 to 58 to 48 to 40, and then when we try it for 10 rounds, it will keep going down and down. And then I'm using this plot.scatter function to get a scatter plot of my latest version of the data frame, which is over 10 rounds. And looking at it, you see that as we increase the number of rounds, the probability of survival goes down. Does that make sense? I hope so. So, do you have any questions about example 1? I'm not hearing anything, and I'm not seeing any questions in the chat box, so I think we are good. Example 2. What will be the probability of constantly throwing an even number with a d20 in 2 rolls, 5 rolls, 10 rolls, and 15 rolls? So for those of you who do not know about a d20, this is a d20. This is a die with 20 faces. And the way it works is very similar to a d6 or regular die that you've seen. I don't know if people use it for other games as well, but I know for sure that people use this for Dungeons and Dragons. And this is just a way to distribute the probability over 20 values rather than 6 values. So, we want to know what will be the probability of constantly throwing an even number. Let's see what we have. Again, I have 2 empty lists, one for number of rolls and one for props. For I, in range of 1 to 16, no, you're going to be fine, don't worry about it. So, we are asked to try it for 2, 5, 10, and 15. So let us give it a try with 3. For I in range of 1, 2, 3, by steps of 1, I'm going to append I to my number of rolls, and I'm going to take 1 over 2 to the power of I. The reason that I'm doing that is that in every roll, I'm interested in getting an even number. On a d20, how many even numbers do I have?
10.
10. How many numbers do I have? What is the size of my space?
20.
20. So 10 over 20, or 1 over 2, is the probability of getting an even number in every roll. And I'm taking that to the power of I because I want to get them back to back. So after the first even number, I want the second even number. Then I want the third even number, and so on. So then I am creating a data frame. I'm calling that DRDF. And when we run this, you will see that on the first roll, I have a 50% chance. And on the second roll, I have a 25% chance. And then if I increase this to 6, I will see that for 5 rolls, it keeps going down. And actually for 15 rounds, it becomes basically 0. So if I plot it, you will see that almost after 9 or 10 rolls, statistically, the probability of keep getting even numbers becomes 0. What is the meaning of that?
You're likely to roll an odd number as you keep on rolling.
Exactly. And if someone comes to you and tells you that I can roll a d20 20 times and every time get an even number, what would you say?
Not likely.
Not likely. And then you are going to ask him to do that with your die because there is definitely something wrong with his die. Yeah. So, actually do not even ask for videos anymore because they can easily manipulate them. So that was what I had for the second example. Do you have any questions? Ramen Man, I really love your jokes. So, for exercise 1, we've asked you to compute the probability of throwing a perfect 20 with a d20 for 2 rolls, for 5 rolls, and for 10 rolls. What is a perfect 20? Yes, the chances of that is 1 over 20, and yes, landing d20 on the roll. So what are the chances of throwing a perfect 20 twice back to back, 5 times back to back, and 10 times back to back? So that is something that you will do for exercise 1. It's gonna get worse than that, Rami. So because it will be 1 over 20 multiplied by 1 over 20. And that will be 1 over 400. that is going to be a very, very unlikely event to do for 10 rounds. So, example 3. What will be the probability of throwing at least 1 6 with a d6? So, we are interested in getting at least 1 6 in 2 rolls, in 5 rolls, in 10 rolls, and for 50 rolls. So, what I'm doing is very similar to the previous examples. I'm creating 2 empty lists. For 2 rolls, I'm setting my range function to 1, 3, and 1. I'm appending I to my list of n rolls. This is the part that is a little different. So, if I'm interested in getting at least 1 6, I am basically only not interested in the other. Okay, let me rephrase that. What is the probability of not getting a 6?
5, 6.
5 out of 6. So 1 minus 5 out of 6, what is that probability?
1, 6.
Yeah, I know, but
The probability of getting 6.
yes. So the probability of getting at least 1 6 is 1 minus 5 over 6. This is the only difference between this example and the previous ones. So in this one, we are going with 1 minus 5 over 6, which is the probability of not getting a 6. And we are multiplying that by I because of the back-to-back nature of the question. So we want to go from event 1 to event 2 to event 3 back-to-back. So I'm defining this one as rolls df, and if you run it, you will see that on the first roll there is an almost 17% chance for getting at least a 6. And then if you go for roll number 2, it is increasing to almost 31%. Does that make sense to you? And Braden, that is correct, yes. So I want one of you to tell me why, in this case, my probability is increasing. Max, that is just another way of looking at it. And yes, Brandon, that's what I was looking for. So if you want to get at least 1 6, the more you try, the higher the chances or probabilities of you getting that 6. So if you look at the nature of the problem between example 3 and example 1 and 2, you will notice why the probability of some of them goes down by repeating and the probability of some of them goes up by repeating. There is no certain carved into stone rule for the probability of an event going up or down over time and by multiple trials. It really depends on what is happening. So try to imagine physically what is happening in that trial, in that experiment, and that will give you a very good idea. So, cool. If we go and give that a try for 5 rounds, you will see that it keeps going up. In the 5th roll, there is an almost 60% chance of getting a 6. For 10 rounds, that goes up to 84%. And for 50 rounds, which I'm going to plot as well, okay, you will see that practically after 30, 35 rolls, it is inevitable that we're going to get a 6. So the probability gets very, very close to 1. So similar to the previous one where the chances would go to 0, and this one the chances will go up, but it gets close to 1. Remember that a probability is a value defined between 0 and 1. We do not have a probability more than 1, and we do not have a negative probability. So, do you have any questions about example 3? Nothing coming through. I hope that is a good sign. For exercise 2, we have asked you to compute the probability of throwing at least one perfect 20 with a d20 over 2 rolls, 5 rolls, 10 rolls, and 50 rolls, and we want a scatter plot for 50 rolls. Given by how example 3 worked out, do you expect the probability to go up or down?
Down.
Why?
Up.
So I heard it down first. Tell me why you think it will go down. No? Okay, who said up?
The more times you roll the die, the more likely you'll end up getting a 20 at least one of those times.
Exactly. Exactly. So, if we want to move on to exercise 3, by nature it is very similar to exercise 2. But we will talk about the differences. So it is asking, what is the probability of drawing an ace at least once? So how many cards do you have in a standard deck of cards?
52.
52. Good, good. I see that we have a lot of people familiar with cards. That is good. Max, was it you who used to live in Vegas on Tuesday? One of you were very familiar with Vegas rules. I can't remember the name. But it's all right. Yes, we have 52 cards. So if I want to... Oh, it was Ben. Okay. So if I want to draw a card, what is my space sample?
52.
52. If I'm looking for 2 of hearts, how many outcomes am I looking for?
1.
1. If I'm looking for an ace, how many outcomes am I looking for?
4.
Yes, exactly. And I see that Jacob answered me as well. Thank you. So, the probability of drawing an ace at least once. I think that now that we have talked about how many aces we have, how many cards you have, you will have a good chance of tackling this on your own, and it is very similar to exercise 2. Do we have any questions about cards? Okay, so example 4. It has multiple parts, and I hope that it will remind you of your question number 2 on your take-home part. I don't know how many of you will consider that as good memory and how many of you will consider that as bad memory, but I just hope that it brings that back to you. So, example 4, part A. Write a function to find the probability of an event in percentage form based on given outcomes and sample space. What have we done? I'm creating a function. Okay, let's hold it there. I've been grading your papers, And something has stood out for me that I wanted to discuss with you for a while. Guys, when we ask you to define a function, what do you think we mean? Use def and return, yes. Use def and make a function. Yes. Surprisingly, I would say maybe less than 5% of you have done that on your exams. What you have done in many cases were correct, but it was not a function. You had the content of the function just out there. So there were no name, no def, no column, no asking for inputs. And I was quite surprised because during the labs, it has been multiple occasions that we have defined the small or large functions. So from now on, please remember that when you are asked to define a function or to create a function, you need to go with this format. So what do you see here? We see def space, the name of the function. Since we are defining this function, this is a user-defined function, we can name it whatever we want. I'm naming that prob, you can name it whatever you want. Then open parentheses, the inputs that you want for that function. In this case, I have outcome and I have sample space. This is because the question asked me to find the probability of an event in percentage form based on given outcomes and sample space. So I'm asking for 2 inputs for this function. And then close parentheses, column. Then I am defining a local variable. I'm naming that probability. And that will be equal to outcome divided by sample space multiplied by 100. Why am I multiplying it by 100?
What percentage?
Thank you very much. And then in the last line, I have return, and I am rounding that probability and sending it out. So this is how I am defining this function. It is not the only way that you can do it. This is the way I am doing it. So whenever it comes to user-defined functions, there is usually plenty of room to be creative and do different things. So that is what's happening in step A. We are defining a function, a probe. Now, part B, use the function and compute the probability of rolling a 4 with a d6. So, rolling a 4, how many outcomes is that?
1.
Only 1. Rolling a d6, how many sample size do I have? Like, what is the sample size?
6.
6. So, I'm going with outcome equal to 1, space equal to 6, and then I'm asking for my function to be applied on these 2 numbers, and the probability is computed as 16.7%. Does that make sense? Are you following what is happening with this prob function? Yeah. Yes. Cool. Cool. Okay. C. Use the function and compute the probability of drawing a king from a standard deck of cards. How many outcomes am I interested in? Nope. 4. 4 is the answer because we have 4 kings. And that's why I said outcome equal to 4, because drawing a king is 4 of the possible outcomes. What is the size of my sample space? 52. So I set 52 as my space, and then I run it, and it will tell me that there's a 7.7% probability of drawing a king out of a standard deck of cards. So far, so good? Brandon, basically, when I say outcome and SAM space, I am saying that I want two numbers or two inputs, and I want to divide them by this order. What I name my objects doesn't really matter, as long as I'm consistent with their order. You can name them whatever you want later. What the prop function will do is that it will take the first input, divide it by the second input, and multiply the result by 100. Yes. Okay, cool. So let us move to part D. Use the function and compute the probability of drawing the king of hearts from a standard deck of cards. What is the difference between D and C? We have one choice, because in the previous one we just wanted a king, we didn't really care what king. In this one we want the king of hearts, and that is only one of the cards. That is one outcome. So my outcome will be 1, my space will be 52, and my prob will be, actually let me run and make sure, 1.9%. So as you see, there is a lower chance of getting that card, and that is what we would expect. So, part E. Use the function and compute the probability of drawing an ace after drawing a king. So, this morning when I was reading this, I thought that it might be a little confusing, and there are at least 2 interpretations of this, so I added something to my notebook. I think you have this. So one way of understanding that statement is that we had a deck of cards, one king has been taken out, and now what is the chance of drawing an ace? So, by removing a king from my deck of cards, what has changed?
The sample space.
Yes, and what is the new sample space?
51.
51. How many aces do I have?
4.
Still 4, because the card that was removed was not an ace, it was a king. So my outcome is 4, my space is 51, and if I run my prob on that, that will give me the probability. The other way to interpret the question is that I want to know the probability of first getting a king and then getting an ace. Back to back. So, in this one we have 2 draws. For the first draw, what do I want?
A king.
A king. Yes. And how many outcomes will that be?
4.
4. So my draw 1 is 4. And what is my sample space?
52.
52, because that is the original standard deck of cards. On my second attempt, what do I want?
Ace.
Ace. And I'm seeing a 4 in the chat box because I have 4 aces left. And what is my sample space?
51.
51, because I've already removed a card. And what will be the ultimate probability?
The probability of the first one times the probability of the second.
Exactly. But if you notice what I have here, once I run the prop function, I'm dividing it by 100. Because the way that I define the function, multiply each one of them by 100, and then if I multiply the results, that will be wrong. So I'm getting the probability of the first draw, dividing that by 100. I'm getting the probability of the second draw, dividing that by 100. I'm multiplying the 2 of them, and at the end, I'm multiplying them by 100 to get them in percentage form. Does that make sense?
Yes.
Okay, so if I run this, on the first case, the probability of drawing an ace, given the deck has 1 less card, is 7.8%. The probability of drawing a king first, and then an ace, is 0.6%. Does this make sense to you?
Yes.
Yes? I need more yeses for this one. Okay, cool. This is actually a very important example. If you get the concept of this, if you understand what is happening in this, you have this lab. So let us go and see what else we have. On F, use the function and compute the probability of drawing an ace after drawing an ace. Again, there can be two interpretations of this. The first one is that from a standard set of decks, we have removed an ace, and now you want to know the probability of getting another ace. In this case, how many outcomes are you interested in?
3.
3, because one ace is already gone. What is the size of your sample?
51.
51, and that will give you the prob out of outcome and space. So on the second situation, you want to know basically what is the chance of getting 2 aces back to back, right? So on your first draw, what are you interested in?
Probability of drawing an ace from a full deck.
And how many outcomes will that be? In how many outcomes?
4.
4, because we have 4 aces in a standard set of deck. How many cards do we have? What is the sample size?
52.
52. And then draw 2. How many outcomes are we interested in?
3.
3. What is the sample space?
51.
51. And I do the exact same thing as I did with part E, and I'm multiplying those values, and at the end I'm multiplying them by 100, and the results that I get is that there is a 5.9% chance for the first case and a 0.5% chance for the second case. Andrew, the reason that I have a few different things on my notebook is that this morning when I was looking at the notebook, I realized that there can be a confusion on this, and I added these. So you can go ahead and add it. It is pretty easy. Thank you, Max. So, part E. EF we did. Part G. Use the function and compute the probability of drawing a heart or a club. So you want to pick a card, and you want to know the probability of it being either a heart or club. Why were you dividing by 100? Because, Audrey, when I'm defining my function, I'm multiplying the division of outcome and SAM space by 100 to get the percentage. But if I am multiplying the probabilities, that will cause an error in the ultimate outcome. So when it comes to multiplying, I divide the outcome of my function by 100, then do the multiplication, and for the final output, I will multiply by 100 to get percentage. Okay, and Rami, you're asking for the piece of code. I'm giving you one of them. So, part G, on your first draw, actually you have only one draw. Which one? Mishael? Is what for you?
Let's call that line of code.
The one that I pasted?
Right.
It's part E.
Okay.
Because it's king and ace. That's why you have KA.
Okay.
So, what outcome do you want when you're looking for a heart? What is the size of your outcome of interest?
13.
13. Why?
A fourth of the deck is closed.
Yes, because we have 13 cards with hearts on them. And then what is your sample space?
52.
52. And when you're looking for a club, what is the outcome that you want? How many?
13 as well.
13 as well, because of the same reason. And since we are interested in an or, so we want hearts or clubs, the ultimate probability is the first one plus the second one. And if you run it, you will see that the probability of drawing a heart or a club is 50%. Does that make sense to you? Because we are interested in getting half of the population. Cool. Do we have any questions about part G and why we are summing them up rather than multiplying them? Max, that is correct. Exactly. Okay. Then we get to part F. Before we get to do that, how many of you have played poker? Me, never, ever. No how. Okay. Rami and Hannah, I don't know what you have against poker, but you don't have to lose a lot of money on it. Did you really say that blackjack is superior to poker? We're gonna have some serious problems, man. Okay, I personally have an issue with games that are solely relied on chance. And, yeah, poker is a game of character. But the reason that I'm asking is that in poker we have a term, and it's royal flush. And I'm not from Texas either, but you gotta learn it at one point. Okay, the royal flush is a card like this, is a set of cards like this. Actually, I have given you a hint. In poker, straight flush, including ace, king, queen, jack, and a 10, all in the same suit, which is the hand of the highest possible value. So, no, Rami, don't go and frame me like that. You are all adults, and just playing poker doesn't mean that you have to gamble on it. But the reason that we are having this discussion is that a royal flush is a card set with these characteristics. And in part F, we want to use our function to compute the probability of drawing a royal flush in the same order. And yes, Dr. Cleveland has said that you're already gambling. We're just trying to help you win. So, let's see what we need. So, for part, this actually should be H. Okay. So, in our first draw, what do we want? Do you need a 5? No, there's no 5 here. You need an ace, you need a king, you need a queen, you need a jack, and you need a 10. So, tell me, on your first draw, how many cards you need? We need 5 cards. Yes, Brandon, yes. So we are interested in getting 5 of those cards. And what will be the sample space? 52, because that is our first draw. So 5 and 52. On the second draw, what do we want? Why 4? It is really interesting that your microphones work when they are not supposed to, and they do not work when they are supposed to.
Is that amazing or what?
Isn't it just 4 because you already drew 1, so you just need 4 more, right?
Exactly. So out of the 5 cards that I wanted, I got 1 in the first draw. Now, in the second draw, I'm looking for 4. And what is my space size?
51. Or 52.
51, because you have taken out 1 card. On the next draw, what is the size of your outcome of interest?
3.
3. And the sample size?
50.
The space size is 50. And so on. So for 5 draws, that's what we have. Every time the size of our outcome of interest is shrinking by 1, and the size of our sample space is also shrinking by 1. And we are multiplying those because
it's in like consecutive.
Exactly, because we are getting them back to back. That is why we are multiplying them. At the end, we are multiplying them by 100. Why?
We want the percentage.
Because percentage.
Yes, and we are multiplying that by 4. Why?
There's 4 different suits, so there's 4 different.
Thank you very much, smart girl. Yes, because it can be. They need to be in the same suit, but we have 4 different suits. So that's why we're multiplying by 4. And if you run this, you will see that the probability of drawing a royal flush is this. It is very, very, very unlikely. It's very low. And that is why it is very valuable. Yes, of course there's a chance. I've actually gotten royal flushes 3 times in my life. So it happens.
Except in the presence of money.
Yes. Exactly. So actually, if you look at the way that the ranks of card sets are designed in poker, the more valuable are the ones that are less likely. And that is something that you can do with functions like this. You can simulate processes with uncertain outcomes or experiments and calculate the probability of getting certain outcomes that you're interested in over multiple tries. Hearts, spades, clubs, and diamonds, I guess, max. And now that we are talking about this, I have to recommend you to go and listen to this. So I don't know if you are using Pandora or Spotify or whatever, or YouTube, just go and listen to this. This will be the theme of this lab. So, do you have any questions about example 4? No? All good? This example was designed based on an example by Daniel Poston from DataCamp, and I've given you the link if you're interested in going and having a look at the original problem and example that he has there. So, for exercise 4, we've asked you to use the function from example 4 and compute the probability of drawing a spade card, the probability of drawing a spade card after drawing the queen of spades, the probability of drawing 3 aces back to back, the probability of drawing a 10 of diamonds or an ace or a king. So these are the 4 things that we want you to do with the same function that we have defined. You can actually go ahead and define your own functions if you're interested in, but you don't really have to. Do you have any questions about exercise 4?
Yeah, for these exercises, did you want us to do it, like for B, did you want us to calculate the probability of drawing a queen of spades and then multiplying that by drawing a spade card, or did you just...
Yes.
Okay.
Yes. So that will be a 2-draw situation.
Yeah. Got it.
So the first one is a single draw, the B is a 2-draw, and C is a 3-draw situation. And D is a 1-draw with OR. If you look at example 4, you should have no problem dealing with exercise 4. Max, I think you got your answer, right? Cool. Okay. Now, let us move on to example 5. 2 unbiased dice are thrown once, and the total score is observed. So I have 2 d6, I'm throwing them, I'm adding them up. Define an appropriate function and use a simulation to find the estimated probability that the total score is greater than 10 and the total score is even and greater than 7. Let's see what we've done. So I'm defining a function. I'm naming that dice roll 1. And for input, it is going to ask for number of simulation. One moment. Berlin, what is part D back-to-back? No, as I just said, it's a single draw and it has an OR condition. So you're drawing 1 card, but you want the probability of it being either a 10 of diamonds, or an ace, or a king. For more information, you can check part G on example 4. Cool. So, my dice roll 1 function needs 1 input, and that is the number of simulation. I'm defining a counter with the initial value of 0. I'm defining a numpy array. I'm naming that dice, and that has all the possible outcomes of a die roll. 1, 2, 3, 4, 5, 6. This should be familiar for you from Tuesday. Then, for I in range of number of simulation, so for how many trials that we want, it is going to randomly choose 1 number from my dice array. That will be the simulation of me throwing the first die. Die 2 is basically the simulation of throwing the second die. And on my score object, I'm adding die 1 and die 2 values. So that will be the summation of my 2 throws in each round. Then I'm applying the rule of the game. So if this score or this summation is greater than 10, I'm adding 1 to my count, which the initial value I had defined to be 0. And then I'm returning, at the end of it, I'm returning the value of count divided by number of simulation. This is basically the probability of the desired event divided by the total number of trials. The part that I'm highlighting, do you have any questions from this part? No? Okay. Then I come here and I set my number of simulations to 10,000. That is not something specified by the question, so you can check it for 1,000, you can check it for 100 and see the differences. And then it's going to print the probability of rolling a number greater than 10 after n simulation rolls is my dice roll 1 function applied on how many number of simulations that I want multiplied by 100. And if I do that, you will see that the probability of rolling a number greater than 10 after 10,000 rolls is 8.08%. Do you have any questions about the first part of example 5?
I have a question.
Sure.
What if this 1 after dice comma 1?
This one?
Yes.
This means that I want one random selection out of my array.
Okay,
If
cool,
it
cool,
was
cool.
2, it would pick 2 numbers. If it was 10, it would pick 10 numbers.
Gotcha.
So, what is the significance of count over n simulation? That is the probability of our desired outcome happening. So, using this if part, if block, I'm defining a rule that specifies my outcome of interest. And for every single time that it happens, I'm adding one value to my count. So basically, at the end of the day, the count will be equal to how many times or how many cases that my desired outcome happened. And I'm going to divide that by the total number of trials, and that will give me the probability. Max, I hope that was a good enough answer. Braden, I ran something for 1 million trials and my computer didn't explode. No, it's not going to explode. It may just take a while. Why did we add a 1 to the count if the score is greater than 10? Kalian, these are, count and score are very different. So in this line, I'm simply setting a condition that specifies what I'm looking for. What is my desired outcome? What is the outcome of interest for me? And for every time that this condition is met, I'm adding 1 to my counter. So my counter is basically just sitting there and saying, okay, out of this 10,000 times, how many times did you get the desired outcome? I hope that was a good enough answer. Brayden, the amount of times it happens over times tried. Exactly. Exactly. So do we have any other questions? And this is great that you ask questions because that gives me the idea that you are following it. And it is really important that you understand them during the lab because then you will have no issues working on the exercises. Okay. What was the second outcome? The total score is even and greater than 7. So the good thing about the way we are setting this up is that we can apply any kind of condition that we want and it will work the same. So I basically copied and pasted my dice roll 1. I changed the name to dice roll 2. It is still asking for the same input. My count is equal to 0. My dice array has not changed. Basically, up until here, everything is the same. But in this case, the condition that I'm looking for is that the number is either even or greater than 7. So the first one, the score percent 2 equal 0. This simply means that I'm looking for numbers that if I divide them by 2, they will have a remainder of 0. Sorry. So that is another definition for an even number. Or that number is greater than 7. So if I have a number, let's say 9, that is not an even number, but it's greater than 7, it's going to be included as a desired outcome. And then whenever that conditions are met, I'm adding 1 to my count and a similar story. And if I run this, the probability of rolling an even number or greater than 7 after 10,000 rolls is 66.7%. It's a way higher probability. So, do you have any questions about the second part of example 5? Or basically about this part that was different? Cool. So, this example is based on a problem designed by Elliot Soslow from medium.com. I have also given you the link for that. So if you're interested, you can go ahead and check out his blog. For exercise 5, we are asking you to, based on example 5, find the estimated probability that the total score is less than 3 and the total score is divisible by 3. Divisible. So, in the first one, you're basically looking at 1, 1, 1, 2, and 2, 1. And let me, actually, I want you to go ahead and change that to less than or equal to, and make that a little more probable. And the second one is basically you want numbers that you can divide by 3 with no remainder. So you're looking for a total of 3, a total of 6, a total of 9, and a total of 12. Do you have any questions about exercise 5? No? All good? Okay, so example 6. It is almost impossible. That's over 1,000. You can actually go ahead and give that a number that you want. I usually go with 10,000. You can go with 1,000, you can go with 1,000,000. It depends on how patient you are and how much you want to wait on it. 10,000 is a good number usually. So, it is almost impossible to look at probability examples and problems and do not see an example similar to example 6. So since I didn't want you to miss on anything, I added one of these to the notebook as well. So we have an urn, we have a container with 10 white balls, 20 red balls, and 30 green balls. We are going to draw 5 balls with replacement. And we want you to use a simulation for 10,000 trials to find the estimated probability that we draw 3 whites and 2 red balls, or we draw 5 balls of the same color. Do you understand the question? So, a container with 60 balls, 10 of them are white, 20 are red, 30 of green. We are randomly picking 5 balls. We want to know the probability of drawing 3 white and 2 reds, and or drawing 5 balls of the same color. So let's see what we have. First, I am defining an empty dictionary. This dictionary is going to be very useful for us in associating numbers and colors for the balls. So, for I in range of 0 to 60 with range of 1, this 60 is the total number of balls. So if you had 100 balls, this would be 100, or any other number. For I less than 10, we want the string white to be attached. If for I greater than 9 and less than 30, we want the string red to be attached. And then for all the other values, we want the string green to be attached. Look at this part that I'm highlighting. Tell me what is happening.
For the first 10 values, 0 through 9, it's going to give you white, and then 10 through 30, or 10 through 29, the next 20 values is going to give you red, and then all the other values that it can pick up until 59 is going to give you green.
Exactly. So at this point, I'm basically defining my container. 60 balls in it, 10 of them are white, 20 are red, 30 are green. That's what is happening here. Then I want my number of simulations to be equal to 10,000. And I'm setting an initial value to my desired outcome counter, 0. Then I'm setting a for loop kind of similar to what we did in the previous example. So for I in range of my number of simulations, I am creating an empty list for my draws. At this point, it's empty. For I in range of 5, why 5? Because we are drawing 5 balls. If we were drawing more or less, that will be the number that I would put in there. For I in range of 5, I am appending a random number from 0 to 59 from my initial dictionary D to this list. So when this for loop is over, how many numbers will I have in my draw list?
5.
Thank you. And those numbers are within the range of
1 to 60.
Exactly, or 0 to 59. So once that happens, I'm converting that list into a NumPy array, and I'm going to see how many whites, how many reds, and how many greens do I have. So I'm saying that I want to get the summation of all the values in my draw array that are equal to white to be assigned to my object white. The same thing for my red and the same thing for my green. So far, so good? Brandon, to answer to your question, that would be exactly the same, no difference. So, then, this is the part that I will define the condition of my desired outcome. So, if the total number of whites is equal to 3 and the total number of reds is equal to 2, I want to add 1 to my outcome 1. Where is this coming from? It's coming from here. We draw 3 white and 2 red balls. And then at the end, I'm going to say the probability of drawing 3 white and 2 red balls is outcome 1 divided by number of simulations multiplied by 100%. And if we run it, you will see that in this case the probability is around 0.53. Question: is this number going to remain the same if I rerun the cell?
No,
Why?
because for every simulation, you'll get a different number of outcomes.
Exactly, because of the randomness built into the nature of this trial. So every time we are randomly picking 5 balls out of 60. And depending on what we get, the probability will be different. However, if we increase the number of trials, we are getting closer to one specific number. Or we are basically reducing the variability of that probability. But that is not a concern at this moment. So I want you to look at this cell, the answer for part A, and tell me if you have any questions about anything that is happening here. Questions? Okay, so then we are interested in getting the probability of drawing 5 balls of the same color, 5 white or 5 red or 5 green. So on part B, starting from the top up until here, everything is the same. the cool thing about this script is that you can have multiple outcomes or multiple desired outcomes, and it will look at all of them together. So my outcome 1 is still equal to 0. My outcome 2 is also 0, because in this case I have 2 desired outcomes that I'm interested in. Then I am doing exactly the same thing in this part. So for I in range of n simulations, I'm creating an empty list, calling that draw. I'm randomly picking 5 elements from my dictionary. I'm summing up the values of white, the red, and green and assigning them to my object, white, red, and green. And this is the part that it gets a little different. So this is my first condition, something that I did in part A as well. So if white is equal 3 and red is equal 2, I want 1 to be added to my outcome 1. Then the second condition on part B is that if white is equal 5, all 5 balls are white, or all 5 balls are red, or all 5 balls are green, I want 1 to be added to my outcome 2. And then I can go ahead and print 2 statements at the end. The first one is identical to what we did in part A, outcome 1 divided by n simulation multiplied by 1. The second one will be the probability of drawing 5 balls of the same color, outcome 2 divided by number of simulations multiplied by 100. And if you do that, it will give you the answer. So, any questions about example 6, part A and part B? You can unmute your mics and talk to me, or you can type your questions in the chat box.
Just one quick question. So for where it says draw dot append parenthesis D bracket random dot randint from 0 to 59. For the random package, I'm guessing whenever you put things in parenthesis, it's inclusive, and that's why they put 59 and not 60.
Yeah.
Just wanted to make sure.
Yep. Correct. Any other questions? Okay. So for exercise 6, we are asking you to, based on example 6, use a simulation for 10,000 trials to find the estimated probability that we draw 1 green, 2 white, and 2 red balls, and we draw no green balls. And if you have no issues with example 6, you should be able to ace exercise 6 as well. It's really nothing complicated. So since we are doing great on time, I will ask for another round of questions. If you have any questions about any part of this lab, Lab 11, let me know. Unmute your mics and ask your questions, or type in the chat box. Brandon, yes, that is a Dwight Schrute poster on my wall. There you go. I'm getting a question that says for drawing no green balls, basically your condition will be if green equals 0 in this part. So you will still have green balls in the air. You're not changing that dictionary. All you are playing with is these conditions, your desired outcomes. The rest of it is not going to change. Exam grades, we are working on them. We are hoping for probably 7 days, 10 days. You will be notified as soon as they are ready. Any other questions for me? Okay. So, Dr. Cleveland, I think I can stop sharing. And since you are still the host, you can
shut everybody down. Okay.
Yep.
Well, thank you all for attending today, and have a good afternoon. This lab is actually not that hard. You may have to struggle with syntax, but all the examples pretty much will give you all you need to know to do the exercises. Up to the point, all you might have to do is change a few names in the examples to run the exercises. So, and that's by intent. And we will pick up on Tuesday, continuing along this line of activity. And let's see, I've got 2 minutes. So let's see what is on the schedule for Tuesday. The pseudo schedule, actually. And you can't see my screen. That's fine. Let me get the right one.
Doug, that is a good question about Anaconda. We will probably have a workshop, but we will send an announcement tomorrow.
Yeah, we'll run it out through a Blackboard, the announcement. So on Tuesday, we're going to talk about descriptive statistics. That's kind of deviating from the agreed upon lesson plan of the 1330 project team. So we will actually have to go through whatever is predefined there. But what we want to accomplish is at the end of Tuesday, you'll understand the measurements of location of distribution, such as the mean, the median, and the mode. Measures of dispersion or spread, which you know as variance and standard deviation. There's a few others, but they're all doing the same thing. They're telling how far apart the random things fall, how many dice you have, how many sides on the dice you have, and then a measurement of asymmetry called skew, which is how non-symmetric the distribution is. And that's actually quite important in a lot of engineering probability estimation modeling. Not everything is symmetric, and perhaps you've even experienced it as students when you think of a normal distribution, how they used to assign grades. Anyone who's astute would go, well, we don't have negative grades, but the normal distribution is designed between negative and positive infinity, so how does that work? Maybe we'll answer those questions on Tuesday. Anyway, have a great afternoon and a great weekend, and we look forward to seeing you on Tuesday. I've already programmed the server to receive your exercises whenever you're ready. So with that, I'm going to disconnect. Goodbye.
Take care. Be safe.
Be safe and all that. And enjoy another episode of The Office, Farang.
Sure. Thank
If
you.
you get the right TV package, you can watch it pretty much from 8 in the morning to about 4 in the afternoon.
I usually get it on Netflix.
Oh, that's probably superior because then you don't have to deal with the commercials.
Yeah.
All right. Bye-bye, everybody.
Bye. Take care.
Fuck. Oh, I'm so tired of this class.